Okay, greetings everyone. It's October 1st, 2020, and welcome. I'm Stokes McMillan. Welcome to the fourth virtual first Thursday meeting of the NASA Alumni League. So today we have a speaker, Torin McCoy, and Torin's going to give a very interesting presentation on lunar dust. So Mr. McCoy has been with NASA since 2003, and he's a toxicologist by training. He currently serves as a celestial dust risk custodian within the Health and Human and Performance Directorate at NASA at JSC, and in addition to leading the Environmental Sciences branch. He attended A&M and Clemson University, where he majored in environmental toxicology. So now let me hand it over to Torin McCoy. Torin, it's all yours.
Great. Well, thanks, Stokes, and I appreciate everyone attending today. It's a beautiful day here in Houston, and it's great to be here talking with y'all. Again, my background is, you kind of wear different hats when you're at NASA. I'm branch chief, but I'm toxicologist by training, and one of the areas that I've kind of kept in touch with over the years is the toxicity of lunar dust. So I played a kind of a risk management role in that area, and that's kind of the context for why I'm going to talk to you today. I appreciate the chance to visit. I don't know everyone who's on, of course, but I do know that there are likely to be some folks who have a ton of expertise in this area. So I appreciate that and know that that it's always good to keep learning in this area. So please feel free to provide your insights as we go forth, and I'll be glad to answer any questions toward the end. So I'll go ahead and share my screen and see if we can get this going. And I'll go from the slideshow. All right, is that clear for everyone? Good. So today we want to talk about lunar dust, and specifically lunar dust toxicity. You're going to find as we have this discussion that there are a lot of different aspects of lunar dust that we could talk about. And people will call me all the time and say, oh, you need to be at this meeting, they're talking lunar dust. And I go to the meeting and it's, about lunar dust in seals or lunar dust in some operational, visualization at landing or whatever. There's a lot of areas that don't involve human health and crew health. And so that's something just to keep in mind. This is a diverse topic and involves a lot of different perspectives. And so this is just my perspective.
Torin, we're not showing the full screen of your presentation. It's it looks like the small view.
Let's see here.
There you go.
Is that any better?
Yep,
okay,
that's better.
All right. So as we go forward, I want to just start talking. We're going to talk about lunar dust and where we are for the future and how we're positioned for the future, kind of looking back at the past too. And I think at the end of the day, you're gonna hear a pretty balanced risk perspective in terms of lunar dust and what it means from a crew risk. So I'm going to go on to the next slide, and I'm going to start at a weird point, and it's going to kind of be this is a chance for you to give inputs if you want to offer anything. But we're going to talk about some things that are close to home and some things that are a little further away. So, but the first thing is, does anybody recognize this place? I'm open for people to give their perspectives. All right, well, if I don't hear anybody, it is actually Jacob's Well in Wimberley, Texas, if you know, in the Texas Hill Country. And I put this here. This is one of my favorite places. I'm from the Hill Country originally. And this place, I mean, the science of this kind of karst topography there in the Hill Country, and this kind of sinkhole there, which goes down hundreds of feet into caverns here. And what's really cool about this is an artesian well. And so there has flow that's coming up for the groundwater. So it's the intersection of groundwater and surface water. And I tell you this because this is all the science that goes along with it. But I want you to understand, if you've ever been to this place, or you can imagine, there's a lot of mystery with this as well. Because the science is one thing, but if you go down here, people dive down because those caverns go for miles. And this is just the entrance to to all these underwater caverns, kind of like Cascade Caverns or Carlsbad, that go underground that are filled with water. And divers go down there, and unfortunately, it's so mesmerizing that they get lost in these caverns, and they have to go recover these bodies that have explored these areas. So it has this element of intrigue and mystery to it that goes beyond the science. So we'll go a little further from home. Does anybody know where this is? I know it's hard on the Zoom here, but this is actually called the Nazca Lines in Peru. And so we're a little further away from Texas right now. We're in Peru, and this has elements of science as well. This is kind of interesting. These are sort of anthropomorphic figures that are actually carved into the desert there in Peru. And these people that they carved this, maybe it's 2,000 years ago, 1,500 to 2,000 years ago, made all these shapes. And again, you can understand the science of it. I mean, it is kind of intriguing. They actually have gone there, and what they've done is not stacked up rocks. This is actually the negative impression. If you will, the people had dug into the rock and come into different layers and different colorations that are subsurface that make these incredible shapes. Again, there's a science that you can understand how these were created, and there's many other shapes that you can see from plane. What's mesmerizing, though, the mystery, is that these shapes are so well done. This is just one example, of course, of the monkey, but there are many other shapes, and they only can be fully appreciated from the viewpoint of above. And so the people at that time, there weren't mountains in this area to be able to even see these from above. And so the mystery is beyond the science, is how these people made these unbelievably accurate and sophisticated depictions without having the perspective of being able to look down upon them. So it really has a lot of trust and a lot of mystery there. The reason I set you up on this is it's the same thing when you talk about lunar dust. There are some science elements and some things that we can easily understand about lunar dust. You're going to hear me say today that lunar dust is not a foreign property, or doesn't have foreign properties that we just cannot relate to. There are ways that we can relate to this material. There are ways that we can understand it in our experience base, even on Earth. But at the same time, just like these other places, there is an element of mystery that I don't want to take away, and that I can't take away from this material. And I think that's what kept the intrigue over the years, and we need to recognize that that's part of our story as well. And so keep that in mind as we go through. I'm not going to give you my next slide, which is an executive summary, because we'll get there. And I don't have to. I usually give the executive summary for people who are going to be leaving pretty quickly. But as Stokes said, y'all have the time and interest to listen, so I appreciate it. So where I want to start with this is lunar dust. As there are a lot of voices out there about lunar dust, just like there probably is on this call. There's a lot of people out there. You can talk to various different crew members who actually walk the lunar surface, and you'll get different perspectives. You can talk to a lot of different scientists. You can look through the news, and you can look through on the internet, and you'll find a lot of different perspectives about lunar dust. And there's room for different viewpoints. And so I'm just going to give you a couple here today that I think are important. So, you know, one of the comments, these are people who experienced it, who said, you know what, it smelled like gunpowder. However, we pretty much quickly got desensitized to it. And then there are other people who said there will obviously be variations in this, and we have to learn how to do susceptibility testing before flight. So we just can't rely on going there. We have to know ahead of time. Then again, people said, you know what, there was dust in the mucous membranes. It caused some stuffiness. We had, you know, kind of a scratchy voice, but it really didn't cause an inherent problem that was a big deal for us. In fact, some people said we had more problems with fiberglass insulation than we did with lunar dust. Others said, you know what, this is important. I can't wait. We need to study it to look at silicosis and other types of long-term effects. Others said, hey, look, this wasn't as much a crew health issue, but don't take it for granted from an engineering perspective. This may be a big deal. Some said, hey, this was a short-term, wasn't a problem, but if you had chronic exposure, it may be very different. And the one I wanted to highlight at the bottom was someone who said, you know what, I think that there are some properties that we may not be able to mimic fully. So we just need to be careful about what conclusions we draw. None of these perspectives are right. None of them are wrong. this is the totality of the experience, and again, it leads to the mystery and a little bit of the complexity in handling lunar dust, and I give it the respect that it's due because of these different perspectives. So let me just tell you about lunar dust. So again, I told you it was something that we can relate to. I wasn't exaggerating. We have really good simulants that we have used for lunar dust, for example. It's very similar to volcanic ash. In fact, when they made a simulant, they used Arizona volcanic ash. And you know what? It's a pretty good simulant, depending on what you're looking at, either from the chemical physical properties, from the toxicology. Honestly, it's not out of family. This is something that we can't relate to. There are some properties that it has that are very, very relatable for us in terms of scientific facts. Probably the biggest thing that distinguishes lunar dust is the kind of the enrichment in very fine particles. So when we talk about ISS, some of you have seen the videos where Don Pettit takes his socks off and you see these particles that go everywhere, and people say, oh, wow, what a, that must be, it's gross, and it makes us think about what we were breathing. The truth is, those are boulders. Those are skin flakes. Those are clothing particles, lint. Those are what you typically find with ISS dust, and shuttle the same. But they're huge. You're talking, if you can see them, you're probably talking 70 microns. And so a lot of the things you're talking about are way above 10 microns, maybe 70 to 100 in some cases. That's what you see with ISS dust, and that's what we've dealt with on ISS dust in our experience. With lunar dust, you really are looking at almost the whole population is less than about 2 microns in diameter, and maybe the median of the distribution is probably around 0.2 or 0.3 microns. And then it goes all the way down to some ultrafine particles around 0.02 microns. And so that's kind of the range that you're dealing with. Now you say, okay, what's the big deal? I don't understand about small particles. Small particles, if you know much about respiratory toxicology, those are the things that you can breathe in most deeply into your lungs. So many things get caught in our upper respiratory systems, up in your nasal passages, and they're not inhaled deeply to the sensitive parts of your respiratory system. The very small particles, especially things less than 1 to 2 microns, are the things that you can breathe in deeply, and they can have more impact on your health. Now, the thing to keep in mind is people will say, oh my gosh, well, this is a big deal. Some of these particles that are so small just don't contribute much in terms of mass. And our risk understanding right now is kind of based on understanding about the mass concentration. There's some room for discussion on how best to express the metric, but largely the small particles are many, but they don't have much mass, okay? The other thing about lunar dust that you may have heard is that it has electrostatic charge. I've understood that it's a negative charge, and that the iron content gives it a sense of magnetism, which is of course interesting. One of the things that we have heard a lot about is that, with all the bombardment, these surfaces are just very, very reactive, and they're very energized because people talk about radiation or micrometeorite impacts, and we'll leave that for a second and come back to that belief. And I think it's partially true, but it's partially overstated as well. So with lunar dust, let me talk to you about something. You're going to hear me later on say that lunar dust is about half of silicate. It's half in terms of content. About 50% of it is silicate dioxide. And you might think, well, I'm confused. Again, there's silica in sand at the beach, and there's a lot of different forms of silica. What you need to know is that lunar dust is high in silica, but not all silica is created equal. There really are 2 types of silica. There's one form that is relatively innocuous from a health perspective, and it's called amorphous or non-crystalline silica. And the lunar glass that you have like that, or the olivine, or you've heard of diatomaceous earth if you've done any gardening and those kind of things. Those things have properties, even though it's composed of silica, it doesn't have this crystalline form, and it's non-crystalline, and therefore has much less human toxicity. The other form is called crystalline silica. And crystalline silica, an example of that is quartz, which is something that is very well understood on Earth and is very toxic. Another one that's the more likely form on the moon is actually cristobalite. If you've ever heard, I don't know if anybody who's from West Virginia or who has studied much about the occupational history of America, there was a occupational disaster called the Hawk's Nest disaster that occurred in the 1920s and 30s in West Virginia. And it was a situation where they dug into, and it was a really, really horrific situation in terms of not protecting your workers, who dug into this freshly fractured area of highly crystalline silica in the form of sandstone. And so they basically said, hey, we can make some money off this. They sent folks in, and that sandstone material is 70 to 90% crystalline silica. The health effects they saw were profound. And it didn't take years. It took matters of weeks of exposure, maybe months, but even in some cases, maybe weeks of exposure, where people started to see significant problem, including deaths. And there were several thousands of deaths, even though they weren't well recorded, several thousands of deaths that they think were attributable to a relatively short-term exposure. This is a horrific situation, but it's not the situation we're going to have on the moon. And let me tell you why. If you look at the table, I'll show you that the crystalline silica content of various materials is displayed there. You see the volcanic ash has about 3 to 7%, and lunar dust is right in that range. And this is consistent with the story I told you earlier, that this is a relatable material, not dissimilar to volcanic ash. This means that you have much less potential for serious health effects. That doesn't mean that you couldn't have health concern. It doesn't mean that there's zero health concern. It just means that it's not the same thing as some of these things that you have seen in the literature that caused very acute, notable problems. All right. So the other thing you're going to hear me say today is that I am really grateful to the people who I'm sitting on their shoulders, because we have a group here that has been studying lunar dust for a lot of years. And that started actually, there's probably, I'm just going to go through the recent NASA history since I've been here. But starting in 2005, when Bush had us heading back to the moon, there was this big focus on needing to come up with some understanding of lunar dust toxicity. And so a group was formed in 2005 called LADTAG, Lunar Airborne Dust Toxicity Assessment Group. It included people within NASA, and it also included people outside of NASA, some very good geological experts. It included toxicologists, but it also included geologists and chemists and flight surgeons. And I really think it was a really great interdisciplinary team. That group was well funded, and again, I give credence to the people who actually went and lobbied for those funds to study this. And the studies went on almost a decade, about 8 years, and they were really, everyone had a role. The geologist's role was to basically understand, how do we bring up a representative lunar dust sample for these LADTAG purposes of understanding the toxicity of dust? How do we come up with a dust like that? What properties of it do we need to characterize? And then how should we prepare it? I mentioned the surface reactivity and other things. How do we duplicate some of that? This was a big deal, and especially the duplication of the surface reactivity, because the people said, well, you know what, we have native things in curation, but maybe they've lost that energy after all these years of being brought back. We try to do the best we can, but maybe they've been pacified. And so they found ways to basically grind them to activate it, if you could, just like I described to you with the hawk's nest situation, to kind of grind them in different methods to activate those dusts and return some of the in situ properties that they thought they might have. Then what do the toxicologists do? Toxicologists are saying, how are crew exposed to lunar dust? And what are some risk assumptions we have to take into account? What are the routes that they might be exposed? Skin, eyes, inhalation? And how toxic is this? We have well-studied reference dusts, for example, quartz and titanium dioxide, which form kind of a boundary, bookends of very toxic and very non-toxic dust that are similar. And how does lunar dust compare? And then what would it do to lunar dust if we studied it in rats and some animal models? What could we learn about that, and how could we extrapolate those findings to come up with a standard? All these folks work together to get at risk, and ultimately that's what occurred. So what you're going to hear over the next couple slides is just what we found out during those periods of time, and ultimately it led to some exposure standards. So let me just tell you what we found out about lunar dust. So first off, I'll start off with some of the easier things. So people have said, oh my gosh, this is going to be a huge, it's sharp edges, if you get this in your eye, this is going to be just unbelievably traumatic. And there's reasons why people say that, I understand, But what we actually did, we used a rabbit model, which is the standard model that the toxicologists use when they're trying to understand ocular risk. It's a very good model. They started off and they put at a certain level in a very first tier to look and see if there was any chemical irritancy. Is this very chemically reactive? And what they found was that there really wasn't. And so they did that before they put it in the animal's eyes. That ethically, they used some cultured cells, and they didn't see any evidence of that. And when they looked at, and they realized there was no chemical irritancy, they looked at mechanical irritancy. So what happens when you put it in your eyes? And the Dre's test is what this is called. And what they actually found is this activated dust that was jet milled and tried to be activated, and as close as the geologists could come to replicating conditions on the moon, it really had a relatively mild amount of redness and swelling in the eye after an hour, and really resolved itself within 24. So what this tells you is an animal tests are confirming generally what our crew told us in Apollo. Yeah, there was a little bit of an eye irritation, but it really resolved itself. This is not a continual issue. The other thing is skin rest. This was actually led by the folks at Ames. I should say, by the way, this wasn't just a JSC effort. This was folks at Ames and Glenn and other places who were significantly involved. The folks at Ames, again, it's about half silicon dioxide, and they found that it was actually really abrasive, and that's not surprising to anybody, right? So you could damage the skin, not just by touching it, but especially if it got in your suits or your gloves, and you were doing a lot of movement with it. You can understand anybody who's been to the beach and done much work along. You can see where this could be a big deal under your fingernails or any place where you're having to get it where it could irritate you and rub, especially with mechanical movement. So this is an abrasive material, and that's good to know as well. So I'm going to focus now on the animal part, and specifically mostly the inhalation part. So what we did was we set up studies with rats where they were exposed in different means. I won't go into all the details because you probably don't care about that. But there were different ways that the rats were exposed to the actual lunar dust, and it was native dust. In other words, no activation, and then it was dust that was activated in different ways. There was also dust that were these reference dusts, quartz, which is high in toxicity, titanium dioxide, which is low in toxicity. And there's different ways that we use this to try to understand. We actually started with an exposure. There were 6 hours per day with the rats. They breathed it 5 days a week for a month. And so this is a fair amount of work and a lot of setup and a lot of investigations. And so we used different dosing levels with actual lunar dust again. And then we looked at the pathology afterwards to understand exactly what happened. And so what we actually found was that there was a concentration-dependent increase in inflammation biomarkers, and there was some histopathologic changes in the lung. So there was health effects for the animals that were exposed above 6.8. 6.8 was milligrams per cubic meter was the exposure amount where they found it to be no observed adverse effect level. So this is the level where we were able to not see problems with the animals that were exposed, but importantly, you saw problems for the levels above. So this is a great tox perspective you need, because it gives you an idea about the dose response, but it also gives you a point where you don't have any toxicity. And there's different ways you extrapolate from this no effect level. But what we did was we took into account the exposure time. We took into account some understanding about interspecies factor. But by the way, rat are actually a really decent model for the human lung. And so there's not a lot of uncertainty in that area, only a small interspecies extrapolation factor, some margins, some uncertainties that we incorporate to make sure that we're protective. And then we incorporated a factor to account for the fact that we're extrapolating up to 180 days in this instance, whereas the studies were only for a month. And so we ended up getting, what you have here is a limit, an acceptable limit of 0.3 milligrams per cubic meter, okay? And that's the amount for lunar dust. So I know I went to some detail, and you may have not cared about some of these things, but let me just tell you the takeaways again. What we actually found was that lunar dust was relatively somewhere between quartz and titanium dioxide in terms of the toxicity. And so when originally they started this, people weren't quite sure. They had about a 300-fold range amongst the experts of speculation about where the ultimate levels would end up before they started any of the studies. And what we actually found was it probably, maybe it wasn't all that surprising. It was somewhere in between innocuous and toxic. And so that's the good news. Probably more towards the quartz end, but some of this has to do with the uncertainty factors that are built into it. But this kind of shows you a PEL is a permissible exposure limit. And we ultimately set an exposure standard based on that, and I'll talk about that in a second. The other thing we figured out was this was really surprising. Surface reactivity, remember I told you we grounded all these different ways? It didn't make a hill of beans difference. The data just didn't show. Now we got to be fair. Maybe we didn't do it well, but these geologists were smart and they studied it for a lot of years, trying to activate those surfaces. And it didn't matter what happened. The toxicity wasn't dependent on how you activated or didn't activate it. So that was the key takeaway. The other thing is that the ocular dermal risks are really manageable. They're something that we can understand and deal with. And I'll talk in a second about no other chemical concerns. So really the focus was on lunar dust itself and not the particles that may be retained within the matrix. So this is how we ended up with, we set a standard in about 10 years ago, it's actually more about 7 years ago. We set a standard here that said that the system shall limit lunar dust particles less than 10 microns in size in any habitable atmosphere below a time-weighted average of 0.3, which is what you saw from the studies, during these daily exposure periods that may persist up to 6 months in duration. And again, we'll talk about a little bit later that this is different, of course, for Artemis, but this is what we put on the books. So I mentioned other constituents, and you said, well, I'm confused about why you mentioned that. Just like, if you recall, we talked, anybody who's done any paying attention to the literature over the past 5 to 10 years, when we were talking about an immediate Mars return, there was significant discussion and hype in the media about, and from well-intentioned scientists who were saying, oh my gosh, we have huge amounts of chromium there. This is hexavalent chromium. This is going to be what you have with Aaron Brockovich and those situations with groundwater contamination. We have perchlorate. It's just going to be so toxic, such an issue. Those things, and again, we can talk about that. A lot of that was overblown. Some of it had some truth to it, but you don't have all those same concerns for the moon as you had for Mars. Perchlorate is a legitimate concern with Mars, although a manageable issue, but it's a legitimate concern. You don't have that same concern with the moon. There's just less free chlorine. There was a reducing environment. It's different. So there's just not the same types of situations where you're going to have perchlorate concerns. And then we looked at it. There is chromium, and there is things like manganese. But really the levels are not that different from what you see in dust here on Earth. We have those same compounds on Earth. And the chromium is present in a trivalent form, which is not the toxic form. The trivalent form is the form that you get if you drink a beer or if you take any chromium supplementation. Chromium picolinate, for example, is trivalent chromium. Very non-toxic, actually very healthy for carbohydrate metabolism. So we did some risk assessments, and we said that any particles that are retained on the lunar dust, for example, chromium or manganese, really aren't going to be the drivers. The driver is going to be the dust itself and what effect it could have on your lung. Again, I'm not saying that it's a severe issue. I'm just telling you that's where our focus lies, on regulation of lunar dust itself and not some of the particles within the matrix. Okay? So all this said, where are we at now? So I've caught you up to speed on what we know. So we're at the fulcrum here, and we're moving toward what we don't know. So we're looking ahead at Artemis and looking back at Apollo, looking back at our lag tag studies, and people are saying, what do we need to do to understand this? And so we're going to talk in the next few slides about what is still out there ahead of us. And some of the things I'll mention just quickly. One of the ones is surface reactivity. I only say this. I told you that before, that we couldn't make anything be more reactive such that it was really causing the toxicity. The thing I'll tell you about is people keep saying this, though. They keep you talking a lot about all the reactivity. Keep in mind, when we saw quartz, it was the most toxic of the dust we studied. It was also the least reactive. So the reactivity is not the limiting factor or the determining factor that causes toxicity. Now, the reactivity may affect other systems. I don't know if there are certain things, maybe for some mechanical systems or computer systems. I don't deal with that. I don't have to, so I'll leave it there. But those questions keep coming up. We just haven't seen it. Maybe we didn't do a good enough job, but I doubt it. So that's where we're at with this. the next thing we're going to talk about, I'm going to spend more time on this in the next slides. I won't go into it, but we're not going back to well, in theory, we're not going to be going back to the equatorial regions, and we're supposed to be doing a South Polar investigation. And I'll talk about what the implications are of that, because it's very different, and some of the exposure assumptions are different. And then I'm going to talk about acute toxicity. I haven't talked about that in detail. Most of the studies I'm talking about are generally talking about, up to 6 months, 1 to 6 months exposure. We'll talk a little bit about any acute toxicity potential. All right. So, lunar dust. What I didn't tell you, I should have mentioned earlier, when we studied lunar dust, the geologists thought through and looked and said, what material should we use to give to the toxicologists to do their exposure studies with rats? And they determined that Apollo 14 soils were the right mix, and we'll understand that in a second. But when they make that recommendation, so you can see here in the orange box is where Apollo 14 was taken from. And it was generally, again, in the equatorial area, and you can see it was mostly in the Mare regions. These are the dark areas, a lot of basaltic qualities, higher in iron, manganese, titanium, some of the metals, but very different from what you would get. You can see the depiction here of the lighter areas that you would have. These are the highlands areas that we hear about. This is where you have the heavily cratered. You have the areas where you have the permanently shadowed areas. We'll talk about that later. And so you have these areas that are actually retained here are very different from the Mare areas in certain qualities, okay? And so these areas, there's more aluminum and calcium, and just much different conditions than what you have with the Mare. So most of our experience space is in this area. We do have at least one sample, I think Apollo 16, that was more of a highlands quality, but this is generally what you have. Most of our data actually came from more equatorial areas. So we go to the next slide. So I tell you why they recommended Apollo 14. Apollo 14 is, if you see this continuum here, it graphs iron oxides and aluminum oxides, which again are two of the distinguishing factors amongst the soils, the lunar regolith. And what you actually find is that up here in this corner, again, the higher iron content is the Mare, and you see much lower levels down here, higher aluminum, less iron. The dot right here is the dot that we used for the animal testing for our exposure standards. And what I'm telling you is that it's in the middle. It tends to be called a mingled sample, meaning that it has intermediate properties. Now you say, oh, well, why is that important? In risk assessment, you generally don't want to just simply go to the extremes. If you do that, there are situations where you could, but it limits the ability to extrapolate to conclusions. So in risk assessment in general, you want to use some more of a central tendency type values, and you combine those in appropriate ways so you have the right level of protection. So actually, the use of a Apollo 14 soil, even though it's not necessarily a highlands, it's not the highest up here on the Mare areas, it's a good representation for risk assessment purposes. So what I tell you is when someone says to us, oh, we must, we have to start all over because now we're going to go to the highlands, which are at the soils at the polar areas. We have to start totally over, spend another $1 million or $1.5 million to redo the study. Let me just be blunt. If I was into just setting up my research dynasty, then that's what I do. But I'm not that way. I am an optimist, and a pragmatist, and someone who wants to use information we have rather than just duplicating it. I'm also a minimalist, so I don't like to just spend the government's money if we don't need to. And so in this instance, I feel, and my folks feel, that this conclusions that we did that was based on Apollo 14, that the people that came before us, the geologists, knew what they were doing, and we were getting reasonable values that could be used even if we do missions to the highlands. One of the things to keep in mind is our exposure standards, this is a secret, our exposure standards aren't thresholds. No, we're not setting limits that if you go above that, you're going to have serious problems, and as soon as you leave that level, that this means that the crew are at health threats. These are general values that guide how you do business in spaceflight, and so they are not thresholds. And so it gives you a little bit of margin in this. This is not something that is that type of a risk, and that's not the way we manage the risks. So I mentioned Apollo 14. This, you know, this you're gonna laugh at me. Some of you, and some of you may be geologists, and say, oh my gosh, Apollo 14, Apollo 16 soils, the Mare and the Highland, they're just so different. And it's kind of like everybody says, they got the more you're familiar with something, the more you see differences. But at some things that people make a big deal about, the geologists might make a deal, but from a tox perspective may be irrelevant. And so what you're going to see here is that I mentioned silicon dioxide. You can see that this is Apollo 14, the level used in the lag tag testing. This is where probably the best representation of what you have at the pole. You can see there's a lot of similarities. Titanium dioxide is a little lower here, but you can see that percentage is relatively small to start with. You see a little more aluminum, a little less iron, but overall, you're not looking at something that's totally dissimilar. And so this is why we can do our business, why these simulants do a pretty decent job of representing the tox and representing health risk, and why I feel like we don't have to start over and we can use our lunar dust conclusions that we had from Apollo 14. So just to show you the standards that we had, I will just say that this is the 6-month permissible exposure limit of 0.3, and we proposed limits through different calculations for gateway, which is going to be a 30-day exposure, and then the lunar surface, which is going to be a 7-day exposure. And so you can see that the levels, for example, on the 7-day are much higher because you're having a much less days of exposure. So not all chemicals work this way, but with lunar dust it does. There's the ability to say, if you're exposed for less period of time, you can have a higher level of exposure at any of those short-term points and not cause any difference in the cumulative exposure. So it allows you some flexibility in how you have these standards. You might ask, well, why is the 30-day the same as the 180? The 180 had built into it some assumptions about how regular and how often during the day you'd be exposed, and that you would end up, after 6 months, having kind of a sense of regularity in terms of you have an EVA, the systems clean it out in a certain specified amount of time, and you know what you're dealing with, and the other times the air is totally clean. And so it was more of a different risk assessment concept and didn't really match the mission, especially for these short-term like gateway. We felt like it was not appropriate. So this is more of a continuous exposure. This was more of a incremental parts of a day. And so that's why the numbers are the same, but it's more of a simplifying assumption on how we do business. So, all right. So I mentioned acute problems earlier, and some of you may have been just wanting to biting your tongue because you wanted to say, hey, I've heard that there were significant problems with lunar dust, and that the crew surgeons had real issues with it. You're right. You're partially right. Let me give you the concept. Remember I mentioned to you when I started with Jacob's Well, I don't take the mystery out of this. And so I'm not going to take the mystery out of it with this. I will tell you what the science says, but I'm not going to say that I'm smart enough or we're smart enough to say that there's nothing that we don't understand. So when it comes to immunological issues, let me tell you what happened. There was the accounts written here. There was a crew surgeon, I think it was Apollo 17, I have to remember which missions it was, who actually went through and noted that when this surgeon was recovering the crew and recovering the suits, I believe, that he thought he had allergic symptoms, symptoms like, at first it was stuffy nose, watery eyes, and he actually was smart enough to basically use himself as a study subject, and he started to look look at his own exposures and symptoms, and determined that it appeared that there was some increase in eosinophils, and the lab results that he did on himself showed that there was evidence that this was getting worse with each time. I think there were 3 times that he was exposed, and the 3rd time basically couldn't complete the actions, is my understanding, because of the intensity of the symptoms. Now, when I went to my immunologist looking back at this, I mean, this is pretty convincing. I mean, the data itself is pretty convincing. I have tremendous respect for the person who collected this and made the observations. So what do we know about this? First off, there is nothing in lunar dust that should be allergenic. There's nothing in terms high levels of, for example, nickel or some of the metals that can cause allergenic properties. There's nothing biological that should be in terms of proteins or such that you might have with animal proteins, as an example. There's nothing in it that we would expect to cause this. Now, some folks, and to be fair, all the focus at the time was on lunar dust. And you see the suits with the dust on them. Everybody's aware of it. Could there have been other things? Like I mentioned to you, fiberglass was one of the things. Could there have been other things that were present in the matrix that weren't necessarily because of dust? Maybe there was something else in the bag. Maybe there was something else that was brought back in those suits, and the dust was attributed to it. So it is an association as opposed to a causation. I can't answer that question, and I don't intend to speak to that. There is some evidence in the literature that goes both ways. There's some volcanic ash where there's some studies that show no allergic properties, and there's some that show some marginal data that's a little bit controversial. So what we ended up doing was saying, gosh, who knows? The real issue is people will sometimes say, oh, it's allergenic, and my nose got stuffy or my eyes watered. Well, anybody who knows particles, that may not be an allergic reaction. That just may be your I guess let's say it this way. Your reaction to particles and your reaction to an allergen may look similar. And so on the surface, when people say I have watery eyes, that may be, and some of the properties may be difficult to distinguish whether that's truly an allergenic response or whether that is a situation with just exposure to the particles. So again, I'm not going to take the mystery out of this. It's a very interesting finding. What we ended up doing was we are right now funding our human research program is funding some research to be able to study the immune profile and basically treat it like an allergen profile and see if lunar dust has those types of effects in the typical allergen profile. So our folks are working to develop that. It's a relatively simple approach, and we should be able to get some decent answers. With anything, with allergens in particular, as you know, there's a lot of variation. There's a lot of individual variation. So I don't want to take that away. What we end up talking with our med ops community, maybe what we need to do is just prepare for being able to treat regardless of whether it's just inflammation, and that's because of a physical insult, or whether it's an allergenic response. Maybe, nasal steroids, definitely saline for eye irrigation, those kind of things. Let's be prepared, and maybe we don't have to argue about exactly what is going on in any one individual, because we know that there is an element of mystery. So that's what we have there. The other mystery. This is one that I was really surprised by. I mentioned to you that there's no particles carried on, or other chemicals carried on the particles. I should have said at that time, pay attention for this slide here, because it really is, that is true for the normal lunar dust that you encounter as our crews do EVA. But, and that's a big but, there was a study that was done, the L-Cross study, which was the Lunar Crater Observation and Sensing Satellite. And basically, if you've seen the study, which was done just a few years back, they had this impactor that hit the moon, and they were looking, and one of the things they wanted to look at the poles and see if they were seeing evidences of volatiles like water and hydrogen. And lo and behold, if you know the end of the story, they did see those. And the idea is that there are cold traps that are there, and that houses a lot of the water vapor and allows a lot of those areas to, at the polar regions where these cold traps are more prevalent, it allows those to exist. And so this impactor hit this, you saw this plume. But one of the things that came along with it was people also saw other compounds. And these compounds were not innocuous, and they weren't necessarily great things from a health perspective. Things like ammonia, carbon monoxide, elemental mercury, hydrogen sulfide, methane, sulfur dioxide. Those are some of the more toxic compounds that we deal with. And those were all observed with pretty reasonable certainty in the observation satellites and different techniques they used. When I first heard about this, I was like, dang, that just makes my job so much more complicated. And so I have to figure out how to deal with this. There are some good news, though. First off, in terms of uncertainty, this was a gross study in the sense of you have an impactor that hits the moon and you're observing it at length. And you can see that there are signatures of it, but the actual amounts and what amount of plume it took to cause that signature are not well certain. And so there's actually something that's going to be happening. It's called the Viper mission that is going to be going, I think it's 2023, that is this golf cart size rover that will be on the lunar surface that I think JPL is heading up. And that will be studying it in more detail. And hopefully it has all the equipment to be able to do a much better job of understanding how much ammonia and mercury and all these other things you might actually have. Okay. So here's the other thing. This is the important thing, because it still sounds pretty serious. These materials are not likely to be brought into the habitat. When these materials, the reason that they're still there is that they're trapped in a subsurface sample, or they are in these permanently shadowed regions. If brought to where they have exposure and moved from their native environment, our geologist folks and all the folks that are working the Viper believe those will be lost very, very quickly to the vacuum. And so you are not likely to be carrying those things. I know we think about it like you're at an auto shop or something, and then you're going to be carrying these things back into the office when you open the door. If you know that the lack of convection, it doesn't work that way, and these things are going to be lost and not going to be pulled into the cabin in that sense. These things are going to be very quickly gone, these volatiles. So, but our real concern is, what if we try, as we will, to capture those areas, those samples? Let's say the crew go out and they go to a permanently shadowed area. They use all the right techniques to retain the volatiles. You get it in the container, you bring that sampling container back onto the lander, and then, as it did in Apollo, what if one of them leaks? And what if you're not set up to deal with mercury, which is a tough thing to contain? And all of a sudden you have mercury released into a relatively small cabin. It doesn't take much mercury released into a relatively small cabin to cause a problem. So all this says is that this is not specific to the general lunar regolith surface that the crew are going to be encountering as they do EVAs. You have to try to find this material, and you have to try to capture it and capture it well. But if you do, you better be darn sure that you're containing it, because you don't want this stuff liberated. And so this is probably one of the big differences with this polar volatiles issue. And it's a remarkable mystery and study. No one really understands whether these volatiles came from comets, or whether it's part of the solar wind, or whether it's part of the native lunar processes. And it may vary, and maybe a combination of all, but it does appear to be real. They may offer some ISRU in the future, but we have to be very careful to make sure we understand the health risks as well. I'm almost done. Lunar dust monitoring. This is a big mantra I'm on. When we were in Apollo, there were some gross studies where they tried to find some things, and people can extrapolate some information, but in general, the technologies did not exist to be able to describe how much lunar dust the crew were exposed to. People can make some guesses and all those kind of things, but we really don't know. The monitoring, either an archive where you bring a sample back, or definitely real time. None of that existed at the time, and so we really did not have that. I do not want to replicate that uncertainty and that problem today, or in 2024, 2028. I don't. I like to know things. And so we are trying to get a lunar monitor. There are great techniques today that you can use for lunar dust monitoring, because it's very, very familiar. We do it here all the time in mining and various other applications. We know it well. Aerosols and particulates are a big focus on the Earth. And we know how to do it. So there are various prizes. NASA has actually invested in several. There was a Earth Air Space Prize, I think, that our organization was involved with, and actually identified a couple of novel techniques that some academic groups had started, and those are in development and may be available by the time. And if not, we actually have there's some great commercial options out there. This is just one of them. It's a COTS device, which is called TSI Dust Track. The nice thing about it is this came out of Research World, and so it actually gives you need to have concentration and what particle size. So you need to know how much, for example, particles less than 2 microns or 10 microns, and then you also need to know, you have to have both those to do risk assessment. So you can't just say, oh, well, we saw this many particles. You got to know what size they are. So this type of approach can do it. The nice thing about this, this is the COTS device here. The nice thing about this customized device that I told you now, so this is just one example, is there even smaller. And one of the neat things is that they may be able to help you figure out whether it's lunar dust or whether it is a combustion event. And as you know, we have a lot of false fire alarms on ISS and I'm sure in shuttle. And this might help you distinguish between the two because it works by light obfuscation in both cases. So it's important to be able to distinguish it. So what I tell people with monitoring, there's a pushback. I'm getting pushbacks now, and people say, well, you know, let's see, maybe we don't need it. Maybe we just have the HEPA filtration, which is the high efficiency particulate removal that's very, very effective. If we have that, maybe we don't need monitoring. But I always tell people, you know, if you don't have monitoring, you never really know how good a job you did. All you have is some engineer's calculations on the back of the envelope saying, oh yeah, well, this should have been fine. And in the end of the day, when you actually have the dust brought in from the EVAs and you got all the systems working together and you say, how well did we do? And if we don't have lunar dust monitoring, you say, I don't know. I don't know. And when you're planning Artemis for maybe a 180-day stay, it's important for Artemis, for the second one, for Artemis 2. For phase 2, you need this data. You need to know what kind of challenges you had over 7 days. So we have to learn from this. So we're making a push right now to try to get this added. But you know, there's efforts. They got a lot of other pressures and things that people want to add. But this is a really important thing. One of the things I think it's really, I keep telling everybody, because they say, well, you just said lunar dust was not like some, you know, it's not like ammonia. It's not something that's going to kill you outright. So you know, how important is it? And I said, you know, whenever the crew get there and they start to observe, just like they did with Apollo, and they start to see some dust build up and they see things liberated and all those things, they're going to think, hey, wow, I'm breathing that. And in some cases, it may just be lint. It may be dander. It may be hair or skin particles. But you're going to have to be able to say, hey, look, we have the data to show what you're exposed to. And by the way, this is not an issue. And so we can continue with the missions with some more assurance. The other thing is when they come back, this is one of the obvious challenges. Again, not an unsurmountable challenge, but an obvious challenge with the moon, dust. And it's incumbent on us in terms of occupational documentation. We need to be able to show people what they were exposed to. And that way, if people come back and say, hey, I'd like to look and see how much dust I was exposed to, I'm experiencing problems or whatever, it's nice to have, we need that data. It's incumbent on us. It's our due diligence as someone who's exposing them to that environment. So I think the monitoring is important for those different roles. So I just give acknowledgements to the people that I've worked with on this over the years, and a lot of people helping us understand things. Again, there's a lot of great science, and we got to leave room for some mystery, or we're not doing our jobs correctly, and that's part of the fun too. So that's it.
Well, thank you, Torin. Fascinating discussion. So let me open it up now to questions. I'd like to start out with one then. So it's been, Torin, can you hear me okay?
Yes, I can.
Okay. So it's been 50, 60 years now since the astronauts returned from the moon and all the people that were exposed to moon dust. Can you conclusively say that lunar dust does not cause cancer in these people?
You know, I'm going to be, you said cancer, is that right? So I will say that that's not my job to do. So I will punt on that conclusion. I will tell you this, that as anything, you know, people get really, they get worried with carcinogens and those kind of things. There's no reason to think that lunar dust works as a carcinogen. Moreover, when you're only exposed to the short-term durations you have with Apollo, you know, I mean, benzene's a great example. Benzene is a very potent carcinogen. We get exposed to it every time you fill up your car with gas, but it's a very short-term, and it's not something that's likely to cause problems with you long-term from that route. And it's the same with lunar dust, except for lunar dust doesn't even have the carcinogenic properties to begin with. So I can't say that I've looked at that data. I know that our teams study these things regularly, but this would not have been a big focus on lunar dust, because it shouldn't, the exposure doesn't make sense, and it's not known to be a carcinogen regardless.
Okay, thank you.
Yep.
I've got a question. I don't know if I'm exactly how to ask it or not, but I'm not familiar with the Artemis program. What is the approximate duration of a typical astronaut for, I guess, for one mission or for his life? How long would he be in this environment breathing this?
Yeah, thanks. So I think what we've been told to work towards is a surface stay of about 7 days. And by the way, our data is not fine-tuned enough where it's, if it's 6.5 or it's 8, it's not all that important. But you're looking at generally about a week is what they would be exposed to on the surface. Now, then you would leave that surface and return to Earth. I think that depending on whether you go through Gateway or not, you may be looking at an overall mission time frame of maybe 21 days, something like that. But overall, the actual exposure to the lunar dust should be on the range of a week, and maybe slightly more. Maybe it's 10 days, but you're generally looking at relatively short term.
Okay, thank you.
Yeah, other questions?
This is Phil Engeloff. You mentioned early on issues of possibly individual susceptibility and screening of individuals. I think maybe a comment from one of the Apollo crews. And then in light of the one Apollo 17 flight doc that seemed to show some maybe elevated sensitivity relative to anybody else, are there any further thoughts or hypotheses about, whether certain individuals may have certain reactions, either to chemical compositions or particle size or some reason for screening?
Yeah, so I think it's a great, and I think it's a great question, and I know that I've heard some of our flight surgeons, or at least one of them, who's made good points about that, and I do think it's something to keep in mind and leave that possibility open. As my experience has been, I know with allergens, it's the same with odors, it's the same with allergens. They're just a broad range of individual response, and so it's hard to say, oh no, that's not going to be. I mean, look at peanuts, right? It's hard to say, oh no, for you that's not going to be relevant. There is some fine tuning like that. That's one of the reasons I said we leave some mystery open with that. We want to do these profiles to understand that a little more, to see if that potential does exist. If it doesn't, it might have been. And again, I want to make sure that there were not a lot of people. There was a much larger volume of people, relatively larger than just this one person, right, on the lunar surface, and that was not a common thing that people said. That doesn't mean that it couldn't happen. It doesn't mean that And I think there's another instance where one of the crew members on the surface said, well, I had hay fever symptoms. Again, you get particles in you, and it's hard to know whether what you deem as hay fever is just your body's response to a physical insult of particles. So we may never fully know. These tests will help us understand the immune potential and the allergen potential, and then we'll go from there. And we got to leave enough margin for us to not understand something and have the docs able to address it and mitigate it if it does happen.
I have a question. What was your assumption, and how did you deal with the migration of the regolith when the landing crew goes back to an orbiting vehicle?
Can you repeat that question? It broke up for just a second. My apologies.
All right. So you have the landing astronauts do their EVAs and stay on the surface for maybe 7 days or so, but then they return to an orbiting vehicle. So what were your assumptions as you studied this problem of how much of the lunar dust got to the orbiting vehicle, and it accumulated over many missions?
Yeah, so that's a great point. So I can't say that I've studied it for Apollo to know about what they experienced when that came back. I know when they obviously got into 0G, they saw a lot of those particles liberated again. I can't say exactly that I've studied that for Apollo. For our future, we want to make sure we have HEPA filters. For example, if the lander interfaces with the gateway, there's going to be HEPA filtration, which is very well suited for removing the lunar dust. So the idea is they're exposed at the surface, and then we want to minimize that exposure from that point on. So when it goes back to gateway, we're hoping that the interfaces requirements are very strict, such that you don't have a continuing exposure beyond that to any significant degree. So you're right, it's a good thing to keep in mind. I just don't know what happened with Apollo in that area.
I have a question.
Yep.
The EPA uses linear thresholds for harm from most everything, including radiation. So they say that any radiation is bad and it gets worse all the way up to where it kills you. But a lot of people say that a little bit of radiation is much more beneficial to us than harmful, and other things also. Do you consider any of that in your thresholds? You know, like if you have no particulates, then you go in an area where there's really bad particulates, you kind of get accustomed to it, and it doesn't bother you after you're used to it a while. So there's some amount of particulates in the air that you can breathe with no harm once you've adjusted to it. But beyond that, it gets worse.
Yeah, I mean, so each of those things you're bringing up are good points, and some of them are specific to the insult. Like you said, radiation has its own things. Different carcinogens have their own ways, and I haven't heard that discussion in much in terms of the particle world. Like you said, there are different areas on that, but in general with particles, your body has a pretty good way of dealing with removing particles, and it's generally when you overwhelm that you start to have a problem. So in that instance, in the particle instance, I think it wouldn't work well to think of a threshold, a non-threshold. I think there's always a point where your body can assimilate and deal with the particles, and then when you go beyond it, that's when you start to have problems. So I think that's the best situation that we probably can understand.
But as far as particulates, there's a Dr. John Dunn that worked at Fort Hood with the Army. He wasn't in the Army, he was a civilian, but he's done a lot of work with particulates. You might talk to him sometime.
Okay, thank you. Yeah, there's a lot of good folks that have been doing particulate research. Thank you for that comment. Other questions?
Okay, no other questions? Well, David, on behalf of Torin, on behalf of the National Alumni League, I want to thank you for giving us this fascinating presentation. It's really a good one. I think we all learned a lot.
You know, I appreciate it, and thank y'all for your service, and I hope everybody's enjoying their the next phase of life beyond the NASA phase. So I appreciate getting to touch base with everyone again.
Oh yeah, retirement is as good as they say it is. It only gets better.
Yeah.
And so everyone, I'd like to invite you to join us again. November 5th will be our next First Thursday program, where we're going to have Dr. Scott Greenwald, who's a senior scientist in the NASA Vision Laboratory. He's going to give us a talk on the spaceflight associated neuroocular syndrome. So the SANS, which is where astronauts tend to have degraded eyesight. So that'll be our next topic, November 5th. So to no other comment, that will do it for today. Torin, again, thank you very much.
Thank you, sir.
Okay, so we're signing out.